Organic Chemistry, Part 2. Oh, the functional groups. Now we've been just dealing with hydrocarbons in the last set where we were looking at alkanes, alkenes, and alkynes, the single bonded, the double bonded, the triple bonded ones. But they were all just hydrocarbons. There were no other type of elements in them. Now we know plenty of organic molecules have other elements in them. So we're going to specifically go through and identify these functional groups that can be off of a carbon chain. And they, of course, play a role in their functionality. What do these specific things do? These different organic molecules has a lot to do with having a functional group on it. So up here it shows you like benzene. The benzene ring right here, really, these are all just like carbons and hydrogens. I guess I should write that differently. Like here, this is a CH, this is a CH on every corner. Has the double bond 3 times in the ring. It's called an aromatic hydrocarbon. And they smell really good, but they're also used in industry. The benzene is a solvent. Amines, you probably heard of from biology, like those amino acids have a lot of amine groups in their structural compounds. Alcohols, I'm sure you've probably heard of. There's methanol. Ethanol is the one that's found in like beer and wine. There's plenty of, you could have an octanol. You could have, an 8-carbon alcohol. So there's plenty of different types of alcohols. Isopropyl alcohol is one that you buy at the store. That's rubbing alcohol that you use like to clean out cuts and things. Although I prefer hydrogen peroxide to isopropyl because it stings less, but that's just a little, fun fact. Ethers are used as, anesthesia in surgery and stuff back in the day. The alkyl halides, where they have a halogen attached to the main chain. There's also this group called the thiol, which we don't make this year, but it has sulfur in it. And some of your amino acids have thiol groups on them as well. Those are the building blocks of protein, if you remember from biology. Aldehydes, I'm sure you've heard of formaldehyde. That's a type of aldehyde. Ketones, okay, esters, carboxylic acids. This is the one that we were talking about last week, vinegar. Vinegar is a carboxylic acid, acetic acid, also known as ethanoic acid. And then amides. These ones are really interesting because those actually form those peptide bonds between the amino acids. And since we're pretty much built out of protein, those amide peptide bonds are definitely necessary for us to be able to function and live. So we're going to identify them individually, one by one, going through the chart. And you can always have this chart out as something to use as a study tool and help you as you're doing your assignment. Now the R's up here, all of these R's, what do they mean? Well, this is like the attachment to the rest of the carbon chain. So the R is like the rest of the carbon chain has been attached. Let's look at the first one, halides. Example, the X is representing either fluorine, chlorine, iodine, or bromine. One of them attached to the carbon chain. This particular example is showing you a chlorine attached to a carbon that would be called chloromethane. Methane because it only has one carbon in the example, and then the chloro would be like a prefix on there saying it has a substituent chlorine group off of the main carbon chain. This one right here is called an alcohol. How do you recognize an alcohol? You look for the OH. It's going to be an O bonded to an H off of the main chain. Okay, so that's going to be an alcohol. This one right here, because it's bonded to one carbon chain, we would call this one methanol, because it's like methane, but you've added the alcohol group on it, so you kind of combine it to make it methanol. An aldehyde. Aldehydes are always on the end, and this is how they look. They have a C, this is double bonded to an O, and then an H on the end. So when you see an aldehyde, it's always going to be on the end of the chain, and it's going to be a C double bonded to an O with an H. This one right here is showing you a 2-carbon aldehyde because there's 2 carbons. We have the one here, carbon here, and a carbon here. So that's why it's eth, that's the prefix. The ending on the aldehyde is just al, so it's ethanal. Like I said before, we're kind of skipping the naming, but I have them here in the examples. You won't have to name them for the quiz or anything, but just kind of going through the process for those that are interested. Ketones. Ketones, you have to recognize, are going to be in the middle of a carbon chain. They're going to be between 2 carbons. What you're looking for here is a C double bonded to an O, but it's between 2 different carbons. Can't be on the end. It has to be somewhere in the middle. Ketones, the ending is changed to ONE. In this particular case, there's 3 carbons. You have a C, 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 so that's the prop part, propanone. So it's like propane, and then you take off the ANE and you put one, propanone. The carboxylic acid. These ones are also like the aldehydes, always on the end. Look for the pattern here. How is it different than the aldehyde? Well, it has an OH and a C double bonded to an O. Whereas the aldehyde just has the C double bonded to an O with 1 H. So we have this entire group on the end. We call it, the COOH on the end there. Carboxylic acids are also known as organic acids. This particular case, because there's 2 carbons in the chain, we would change it from ethane to ethanoic acid if it has the functional group on the end. Now, ethanoic acid, that is the IUPAC name. We also commonly call this one vinegar or acetic acid. It has multiple names, but the IUPAC name would be ethanoic acid. All right, the amine groups, like amino acids, you should be looking for nitrogen. Nitrogen's going to be in there for an amine. And it could be bonded in the middle, it could be bonded on the end. But it should only be bonded to carbons or hydrogens here if it's an amine group. Or is it here, this one's showing it on the end where it's an NH2 on the end. You can see in our example we have 2 carbons. Those 2 carbons, of course, make it an ethyl group. And then you put the amine on the end, ethylamine. The benzene ring we just call benzene, so you don't have to worry about a name there. But there are a couple different ways you can draw it. You can draw the full out Lewis dot structure. And actually you can't really tell here, but there's double bonds every other carbon there. But you could draw it the stick figure way where you don't actually put the C's and H's in there. Another thing to realize about benzene, because it has these alternating double bonds, they show resonance. So sometimes they just draw a circle to show that it's equally shared amongst all 6 carbons. So resonance structure, they just draw the circle around it to say, hey, everything's shared equally in this diagram. The last 3 we don't really name in a Chem 1 class, but we still want to recognize their functional groups. Esters are really great. We have a fun ester lab we do in AP because esters have lots of really good smells to them, and they're used in lots of products that need fragrances like candles and lotions and stuff. Well, the ester, as you can see, it's in between carbons here. These are representing carbon chains, so it's got to be in the middle between 2 carbons, kind of like the ketone. But instead of the ketone just being the C double bonded to an O, you also have another oxygen in the middle. So C double bonded to an O with an additional oxygen, that's going to make the ester. The ether is also in between 2 carbons, okay? In between 2 carbons. These R's are representing carbons. The only difference is it's just a single bonded O in the middle. Single bonded O in the middle. That's an ether. And the amides, this is the only other one that has nitrogen in it. So you have amines and amides. The comparison, the difference between the amine and the amide is you're looking for the C double bonded to an O with the N. This particular group together, that makes it amide. In an amine, you're not going to have the C double bonded to an O. It's just going to be C bonded to the N, and the N is either bonded to H's or other C's. It won't be bonded, double bonded to an O like that. So that's a lot, but use this chart and practice with this chart right now. I want you to go through these ones, and I want you to circle any functional group you see and label it. So this is the practice that you're going to do. I'm going to give you some time right now to go do that, about 5 minutes. Look through the charts, see if you can identify the functional groups. All right, let's go over this. Let's see what you guys come up with. This first one in the upper left, right here, this one. Hopefully you were able to circle and see that C double bonded to an O, also bonded to an O in the middle there. What do we call that one? Which functional group is that one? It is, it's an ester. Very good. All right, so there we have bell ring for lunch. Looking at the next one in the top here. Looking for our lovely functional group. I see an OH there. So OH is going to be a what? Which one is the OH? Which functional group? Yes, that's an alcohol. Very good. Exactly right. That would be an alcohol. Looking at the next one over here to the right, kind of going in order. Has a nitrogen in it. So, well, I can use process of elimination there and get down to just amine or amide. So which one is that one? Is it an amine or is it amide? Yes, that one would be an amine. Very good. Exactly right. Now on to, I think, this middle one here. We see it's on the end. We see it's a C double bonded to an O with an H on the end. Which functional group shows that pattern? Anyone? It's an aldehyde. Very good. That's exactly right. Moving on to our next one, aldehyde. This one, look at the pattern here. Yes, there's lots of them that have C double bonded to an O, but this one, it's in between two carbons. If you look on either side, the C double bonded to the O is in the middle. Which one has that particular pattern? That's a ketone. Exactly right. Ketone. Very good. Over here to the left, we have that Br attached to our carbon chain. What would we call that one? Where it's one of the halogens. It's either chlorine, fluorine, bromine, or iodine. Yes, it's a halide or a halocarbon. In this case, yes, we have the hal part on there. All right, this one right here, smack dab in the middle. It's on the end, and we not only have a C double bonded to an O, but we also have the OH. That particular case, what is it going to be? C double bonded to an O with the OH, a carboxylic acid. Exactly right. The next one here, we actually have two in the one over there to the right. Which two are in this one over here? I see two. What could we identify them as? What's one of them? Somebody give me one of them. We see the benzene ring. That's exactly right. What's the other one though? The other one is that OH. What does the OH mean? Alcohol. So we have the alcohol and we have the benzene ring. So we have both in that particular structure. Almost done with our practice here. How about to the lower left? We see that oxygen in between two carbons. What would that one identify as? Now it's not double bonded, it's just an O in between two carbons. That one is an ether. Exactly right, ether. And last but not least, our lower right structure here has nitrogen in it, so it can only be one of two. But you also see the C double bonded to an O in the middle with it. So that makes it an amide, exactly. An amide. So that's one of the things, being able to identify the functional group. Another thing that you need to be able to do on organic molecules and larger organic molecules is be able to look at individual atoms within and figure out what the shape would be around that particular atom. We also are going to look at their bond angles for that particular atom and also the hybridization. So this is kind of practice from before. We're going to recall our Vesper stuff, the valence shell electron pair repulsion ideas, and which shapes we've got going on within these organic molecules. Because some of them are large, but they do have multiple shapes within them. We're just going to break it down to the smaller ones. Like starting over here on the left, this CH2O. We want to know what the shape is around that particular carbon. It has 3 bonded atoms. Look, we've got O, we've got H, we've got H. So we've got 3 different bonded atoms, but we do not have any lone pairs on that central atom. So what would be the shape of the CH2O? I know we have to pull that stuff back. That's a T-planar, exactly right. What is the angle on a T-planar? It's 120. And what is the hybridization when you've got 3 bonded atoms, 3 electron domains? They're sp2s, exactly right. So that's what we would label that one as. That would be T-planar, 120 sp2. Now let's look at this one, the methanol, CH3OH. We're going to identify the carbon and the oxygen here. Let's start with the carbon. Looking at that carbon, how many bonded atoms do we have around that carbon? 4. How many lone pairs around that carbon? 0. So what would be the shape around that carbon? 4 bonded, no lone pairs, that's a tetrahedral, exactly. What's the angle on a tetrahedral? It's one of those more difficult ones, the 109.5. 4 bonded atoms means 4 electron domains. That means 4 orbitals have to merge to form the hybrid. So what would be the hybridization around that carbon? sp3, exactly. Good. Now for the oxygen. Look at the oxygen there. How many bonded atoms? How many bonded atoms on that oxygen? 2. How many lone pairs on that oxygen? 2. So 2 bonded, 2 lone pairs. What kind of shape is that one going to be? Bent. Very good. Now, there's 2 types of bent. This is the one that has 2 lone pairs on it. What's the bond angle for a 2 lone paired bent? 104.5. Good. Now, we have 2 bonded atoms. We have 2 lone pairs. That's 4 electron domains. What would be the hybridization here? sp3. Exactly. See, you guys are getting really good at this. Now let's look at this carboxylic acid. This one's actually called butanoic acid. 1, 2, 3, 4 carbons with the COOH on the end. So that's butanoic acid. Oh, I'm sorry, no. I wrote the wrong formula. This one only has 3 carbons. 1, 2, 3. So this part shouldn't be here. We can erase that though. There we go. That's actually propanoic acid. It only has 3 carbons in it. I thought I put butanoic in there. All right, now looking at the first carbon on the left, what would be the shape of that one? What would be the shape on that one? Looks like it has 4 bonded atoms. It has 3 hydrogen and a carbon, but no lone pairs. So 4 bonded atoms, no lone pairs. That's a tetrahedral, which means the angle is 109.5, which also means the hybridization is sp3. Looking at the carbon on the right there, the one that's bonded, double bonded to the O, bonded to the 1 carbon and the other oxygen. So it looks like it has it's bonded to 3 atoms with no lone pairs. What would be the shape on that one? 3 bonded, no lone pairs. It is a T-planar, and T-planars are 120 degrees on the angle around, and then sp2 hybrids. Exactly right. Now let's look at the benzene ring to the right, the C6H6. C6H6. That particular carbon, what would be the shape there? Yes, it's T-planar. It has 3 bonded atoms around it. If you look, we've got the 1, the 2, and the 3 here. Oop, that one's in the way. 3 bonded atoms, no lone pairs. So that's got to be a T-planar, which is 120 in sp2s, right? We already know this. Getting down to the last 2 examples over here. Looking at the nitrogen in this amine one. This one has an amine in it, NH2. What would be the shape around that nitrogen there? How many bonded? How many lone pairs? That's the first thing you should ask yourself to help you determine the shape. It looks like we have 3 bonded atoms. This is a pyramidal, exactly right, T-pyramidal. 3 bonded atoms, and then the 1 lone pair. That means it's pyramidal. Now, what is the angle on pyramidal? It is 107, so that's good to note. And what is the hybridization here? 3 bonded, 1 lone pair. That means there's 4 electron domains. Yes, it's an sp3. Good. The last one down here, this sort of be like a quick quiz from the last set of notes. It has a triple bond in it. What type of hydrocarbon is that one? Remember, there's 3 types of hydrocarbons. Which one would be this one that has a triple bond in there? It is an alkyne, exactly. Remember, the alkenes have doubles, the alkanes have singles, all singles. So this is an alkyne here. But let's look at this individual carbon within this alkyne. We have a bonded carbon here, a bonded carbon here. 2 bonded atoms, no lone pairs. What kind of shape is that going to be? That is going to be linear, exactly right. And linear has what type of angle? 180, and only 2 electron domains. We've got the 2 bonded atoms. What's the hybridization there? sp, correct. Exactly right. So this is kind of what we did last time, but now we're using it, the same information, and applying it to organic chemistry. So not bad, good job. Now let's look at applying also those lovely IMFs, intermolecular forces and polarity here. So many properties depend on the polarity of the functional group and the chain length. You have more hydrocarbons, it's more nonpolar. You have less hydrocarbon part in the functional group, then it takes on more of its functional groups, IMF. In general though, as you go down the groups, okay, alkanes, alkenes, alkynes, if you're comparing ones that have the same number of carbons around the same molar mass, the intermolecular forces are going to increase. Alkynes are slightly higher than the other two in terms of their intermolecular forces because they have triple bonds in them, and we know those are going to be linear in shape. The linear shape means that the cloud, the electron cloud, is more polarizable because you have two definite ends to it. And you don't have, other ones branching off of it. So the alkynes are slightly higher in terms of their intermolecular forces than the alkenes or the alkanes. Now, as with dispersion forces, LDFs, they all increase as the chains get bigger, as you have more molar mass. So like say a decane is definitely going to have stronger forces than say a propane, one that has 3 carbons versus one that has 10 carbons. The one with 10 carbons is going to have much higher molar mass, so it's going to have a much stronger force. Now when we start looking at the functional group ones, okay? So obviously dispersions are the weakest, dipole are in the middle, and then hydrogen bonding ones get the stronger forces in general. The aldehydes and ketones, also some of the other ones like the esters and the ether and other ones, they fall in the dipole category, where we're going to have the, they definitely are polar, they're not symmetrical, but it doesn't actually have an H to O bond or an H to F bond or an H to N bond in it, so it doesn't qualify for hydrogen bonding. However, if you look over there, the amines, those are H to Ns, so they qualify for hydrogen bonding. Alcohols are O to H's, like water has O to H in it, so those are also hydrogen bonding. And then the carboxylic acid has the OH of the COOH, so that one is also going to be able to do hydrogen bonding. Which one will have the higher boiling point? So in comparing these two, we first have to look at what type of forces does it have based off of what the functional group is attached. So if I'm looking here at just C3H8, that is propane because it's a 3-carbon chain there. And then I have CH3OH. This is an alcohol. Okay. What kind of forces is this one going to have, the hydrocarbon? Because it's going to be like this. We're going to have our 3 carbons. We're going to have our H's surrounding them. This would be the H's to draw this one. This is propane. Is this symmetrical or is it asymmetrical? Is that polar or non-polar? I mean, look at the symmetry here. Cut it this way, is it the same on both sides? Cut it this way, same on both sides. So this is non-polar. Good. So what's its only force that it has? LDFs, or London dispersion forces. Let's look at the other one. You can't visualize it, but you already see this OH on the end, so that tells you a lot. CH3, that's our CH3 group, attached to the O, attached to the H. Okay, this part right here, is that polar or non-polar? Is that symmetrical? No, that one's polar. The OH, the functional group, throws off the symmetry completely. But because it has this O to H here, What type of force, what's going to be the predominant? This one's going to be hydrogen bonding. Exactly right. So out of these two, which one should have the higher boiling point? Which one has the stronger forces holding the molecules together? The methanol, good. So the methanol has the higher boiling point, stronger forces. Has the hydrogen bonding, yes. Stronger IMFs, I guess you could say. IMF. Not that you can see here. I'll erase this so you can see it now. The explanation says basically what we just drew and figured out. The alkane held together by dispersion forces, and the CH3OH is an alcohol held together by hydrogen bonds. Remember, boiling point increases as the polarity gets stronger and the chain length gets longer. The stronger forces there, of course, going to tell us that the boiling point would get higher. That also means, if we're talking about other physical properties, the surface tension of the methanol would be higher and the vapor pressure of the methanol would be lower. Because those are two of the other ones we were talking about when we're talking about physical properties. Boiling point, melting points, those are higher for stronger forces. Vapor pressure is lower for stronger forces. And the surface tension also increases when the forces are stronger. Now let's practice a little bit and identify some of these here. Yes, once again, this is got an extra CH2 here because this is propanoic acid. But let's look at them and decide what their predominant IMF and their polarity is. So CH2O over here to the left. Is this polar or non-polar, first of all? Symmetrical or not symmetrical? Polar, good. Now, looking specifically, it's got dipole-dipole forces, we know. It's got London dispersion forces, dipole-dipole forces. But the predominant one, is it dipole-dipole or is it hydrogen bonding? Which one is it for this one? Do you see an actual H to O in there? No, it's the O is bonded to the C, not to the H. So this one is just dipole-dipole. Polar dipole-dipole, exactly. Now let's look at this one. We kind of already talked about this one, so that one's polar with H bonding, that's methanol. We just looked at that in the boiling point example. How about the propanoic acid, this one right here? Polar or non-polar? Is that symmetrical? No, definitely polar. Now, what is the predominant force? Yes, it has London dispersion and dipole-dipole, but does it also have that hydrogen bonding? It does. Look, we have an O to H right here, so that definitely qualifies for hydrogen bonding. Now for the benzene ring over here, C6H6. What do we got going on there? Polar or non-polar? Symmetrical or not symmetrical? Let's look at the symmetry here. Non-polar, good. Cut it here, cut it here, cut it here, cut it here. It's all symmetrical. Very good. So this one's non-polar. So what does that mean about its strongest IMF, its most predominant IMF? Or only IMF, I should say. Because non-polar only has the one. London dispersion forces, good. How about this amine down here, this NH2? Polar or non-polar? Polar, definitely. That NH group on the end definitely throws off the symmetry. So it's either dipole-dipole or hydrogen bonding for the most predominant force here. Does it qualify for hydrogen bonding? Yes, it does. Remember, it's H-FON. We have H to F. H to O, or H to N. And guess what? We have two of them here. Two H to N's. So it is hydrogen bonding. Yep, yep. The last one down here, this butane. It's a butane because it has 4 carbons in it. Polar or nonpolar for butane? Nonpolar, good. So what is its force? London dispersion, exactly right. So very good job applying those concepts here to some organic molecules. All right, uses. I threw these in your notes for you so you don't have to write them down, but if you're interested in, hey, what are some of the things that these compounds are used for? Hydrocarbons, of course, are fuels. That's our octane, butane, propane, methane, all of those. And a lot of the hydrocarbons are used to make our synthetic polymers, like the plastics and stuff. Alcohols, of course, used in beverages. They're used in solvents, disinfectants, and they are reactants for lots of different reactions. The acids, there's plenty of them in food that we, or drinks that we drink and food that we eat. There's a lot of organic acids in like those Sour Patch Kids that make it really tart. The acid gives it a tartar flavor. There's also acids in like soda and in coffee and in milk. So in food we have lots of acids. The amines, of course, in DNA and also in proteins. So lots of different things have amines in them. Aldehydes are good disinfectives and preservatives. Formaldehyde, is the example for that one. Ketones for solvents, so you dissolve other things in them. And sugars. Esters, like I said before, are good for giving fragrance to lotions and candles and other things. Ethers, anesthesia, refrigerants and solvents, and then the amides. A lot of them are used to make a lot of the synthetic polymers like Kevlar, nylon, like nylon stockings, and other, obviously, pharmaceutical drugs. Now, let's talk about polymers real quick. We'll end with polymers and monomers. Polymers are pretty much the big, huge macromolecules. And you talked about the natural ones last year because you talked about those polysaccharides, the proteins, the DNA. They were all built off of these monomers, these smaller subunits. Like carbohydrates are built off of monosaccharides and disaccharides, whereas proteins are built off of amino acids. So the monomer for proteins would be amino acids. The monomer for DNA and RNA would be those nucleotides, okay? I know that you study those in biology, so it's a good natural example. But a lot of our synthetic stuff is made off of monomers, and it builds these long chains of things. So for instance here, the monomers usually have a double bond, and they're usually some kind of alkene. And you break the double bond. When you break the double bond and attach two together, it keeps forming this long chain. So right here, the monomer for this is PVC pipe. It's like white plastic material. I don't know if you've ever seen PVC pipe. Also here, this is the Teflon, the component that they put on top of pots and pans to make them non-stick. Okay, you can see that it's got a lot of fluorines in there. Polytetrafluoroethene, okay, is the monomer, okay? And as they break that double bond and keep attaching to other ones in the chain, it forms this very, very long, big chain, the polymer. Extremely long molecules consisting of groups and atoms that repeat in a regular pattern. And the monomer is the basic unit that's building the chain, okay, the simple ones that it builds off of. So here looking at this one, polyethylene, which is your basic plastic. It's really just ethene to start. These are the monomers, and like I said, it breaks this double bond and then just repeats and attaches more as it goes along the chain, creating what we use a lot of times are different plastic. Now, polymers can be natural or they can be synthetic, the man-made kind, which are the plastics. Examples of natural nucleic acids, DNA, proteins, other natural ones that you may not necessarily think of, like wool or silk, the cellulose cell walls in plants, like those are considered polymers that are natural. Anything that sounds like, came out of a factory, like nylon, polyethylene, polyester, Teflon, those ones, like Kevlar, that's the stuff for body armor and things like that. Those are all going to fall under the synthetic ones, or the ones that are man-made. All right, so we're going to go ahead and stop right here for today, and we will finish the rest next class.